let's take a look at how to fully conduct a chi-square test for goodness of fit. So in his book Outliers, Malcolm Gladwell suggests that a hockey player's birth month has a big influence on his chance to make it to the highest levels of the game. Specifically, because January 1st is the cutoff date for the youth leagues in Canada, where many NHL players come from. Players born in January will be competing against players up to 12 months younger. The older players tend to be bigger, stronger, more coordinated, and hence get more playing time, more coaching, and have a better chance of being successful. To see if birth date is related to success, judged by whether a player makes it to the NHL, a random sample of 80 NHL players from a recent season was selected and their birth dates were recorded. The one-way table summarizes the data on birth dates for these 80 players. So there were 32 between January and March, 20 in April to June, 16 between July and September, 12 between October and December. Do these data provide convincing evidence that the birthdays of NHL players are not uniformly distributed across the 4 quarters of the year? So essentially, we want to see if their birth date influences their success based on the justification that he had in his book. And so if there was no relationship between their birth month and their success, then we'd expect to see the same amount, an even or uniform distribution amongst all 4 quarters. We'd expect them to be relatively equal across all 4 quarters of the year. So first, we will state our hypotheses and our alpha level in the state section of the test. As you can see, our null hypothesis is that the birthdays of all NHL players are uniformly distributed across the 4 quarters of the year, and uniformly means relatively equal or equal. The alternative is that the birthdays of all NHL players are not uniformly distributed across the 4 quarters of the year, and we will use an alpha level of 0.05. Next, we'll check the plan section and make sure the conditions are met for a chi-square test, goodness of fit. So this is, as we need to say, a chi-square test for goodness of fit. And now we'll check that it was a random sample, 10% condition is met, and the large counts is met. They told us that the data came from a random sample of NHL players, so the random condition is met. The 10% condition, we just have to assume that 80 is less than 10% of all NHL players, which is safe to assume. Then remember, for the large counts, we have to check and make sure all expected counts are greater than 5. The expected counts in this case, our sample size was 80. And if it's evenly split among the 4 quarters, then we'd expect 25% to be in each quarter. So that's why we get the expected counts of 80 times 0.25. So we'd expect 20 to be in each category. Each quarter of the year. And since all of these are greater than or equal to 5, then the large counts condition is met for the chi-square goodness of fit. Next, in the do section, we will calculate the chi-square test statistic and the p-value before we can make our conclusion. So remember, for the test statistic, the chi-square test statistic, we will compare the difference between the observed and the expected amounts, square them, and then divide that by the expected counts and sum those all together to get the chi-square test statistic. For example, in January, for the first quarter would be 32 minus the expected of 20 divided by the expected of 20. I'll do the same for the other 3 quarters. Again, I like writing out the different values here because it tells me a little bit about the data here. You can see 7.2 is the largest value. So the first quarter is contributing most to this chi-square statistic of 11.2. And the second quarter was exactly as what was expected. So we get a chi-square test statistic of 11.2. We use that to find our p-value. So remember, our p-value comes from the chi-square distribution, which is skewed to the right. And we had a chi-square value of 11.2 going to positive infinity. Our degrees of freedom, since there are 4 categories, subtract 1, that's our degrees of freedom of 3. We'll get a p-value of 0.011. I'll show you how to do that in the calculator as well. To calculate the p-value, we'll go to second vars to get the distributions, find the chi-square CDF. Our lower should be 11.2. Positive infinity is our upper. Degrees of freedom was 3. And we will paste this to the home screen and get a p-value of 0.01069 or 0.7. So our rounded p-value is 0.011. Just to give you an idea, this is what the p-value is telling us. It's the probability of this chi-square test statistic occurring, given that the null is true. So what that means in this case is, assuming that each month or each quarter is equal in the amount of NHL players' birthdays, then the probability of this sample occurring that we had of the 80 is 0.011 or 0.0107 is what we had on the calculator. And so you can see it's a very low probability. And so we'll use that to make our conclusion about the null hypothesis that it's a uniform distribution. So in our conclusion, since our p-value is less than our alpha level, we reject the null. We have convincing evidence that the birthdays of NHL players are not uniformly distributed across the 4 quarters of the year. And so that's how we answer that using our p-value. But if you just think about it, just think about how different these numbers were than what we expected. And that should start to raise some concern in your mind. Oh, these 32 is a lot higher than 20, which is what we expect. And so our p-value is just the mathematical evidence for whether we have enough justification or enough of a difference to say they're not uniformly distributed. And so based on this information, our p-value says that we do have enough evidence to say that they're not uniformly distributed. Now I want to show you how to do this on your calculator in a much quicker way. So I'll pull up my calculator here. First thing you have to do is enter your expected values and your observed value, or your observed values and your expected values. So I'll put the observed values in list 1 and the expected values in list 2. So we had the first quarter, second, third, and fourth, and then all expected values were 20 if it's evenly or uniformly distributed. Then we'll go to stat and we'll go to tests. And this is a chi-square test for goodness of fit. So there's 2 chi-square tests. We want to do the second, which is goodness of fit, GOF. Hit enter and it will give us, okay, so observed, I put in list 1, expected, I put in list 2, make sure that's correct. We had 3 degrees of freedom because there were 4 minus 1. Calculate, and it will give us our chi-square test statistic, our p-value, and our degrees of freedom. So if you're doing this on your calculator, you need to make sure you put these 3 things down in the do section on your notes. If you choose to do it on your calculator, then like I said, you have to have those 3 things on your notes or on your answer. But if you get the chi-square value wrong, then if you type something in wrong, you're gonna get the wrong chi-square, you're gonna get the wrong p-value. So to help mitigate those errors, what I want you to do is to start writing out the first couple. So maybe put the first 2 in the last value. Now that's not that important for this one because there's only 4, but sometimes there's a lot more than 4. And so just show that you know what you're doing so that if you get the wrong value from the calculator, you've at least shown me that you know how to find the test statistic appropriately. The second reminder I want to give you is when you're checking the large counts, make sure you're showing or checking the expected counts, not the observed counts. That's one error that a lot of students make. The last thing I want to remind you about is, in this situation, we rejected the null hypothesis, which means we believe, or we have evidence that the distribution is not uniform. If for some reason in the future we fail to reject, if we fail to reject the null hypothesis, that doesn't mean the null is true. It's just telling us that we don't have enough evidence to say that it's not true. The last thing I want to look at is what we call follow-up analysis. And so if the sample data lead to a statistically significant result, we can conclude that our variable has a distribution different than the one stated. For example, that's what just happened. Our p-value was smaller than alpha, so we had a statistically significant result. Then we can investigate how the distribution is different by identifying the categories that contribute the most to the chi-square test statistic. So here's a table I just want you to be used to. We have the categories, and then we have the observed values that you saw, the expected values that you saw. This here is the observed minus expected. So there's a difference of 12, -4, -8. And then this is the factor that contributes to the chi-square. This is observed minus expected squared divided by expected. And so you can see this value had the largest contribution to the chi-square test statistic. And the second largest contributor was the category from October to December. So you can see they're contributing in a different way. This one is a lot higher than expected, whereas this one is a lot lower than expected. So it's helpful to look at the values to see which ones had the largest influence or which ones were more different than expected. So this is the follow-up analysis, what we call it.